Okay, resuming the lecture here. We had some technical difficulties here at the house. So normal faults, the result of extension of the crust. This causes the hanging wall to move downwards. Here we have a photograph where a recent earthquake has happened. The hanging wall slid downwards along the fault plane. This person is basically standing on the very, very top of the hanging wall. Just after earthquakes, we can see sometimes the fault surface exposed at the Earth's surface. And we call this the scarp of the fault. This is an earthquake that you might remember. This happened just last year, known as the Ridge Crest earthquake. And again, this was a movement along a normal fault. The two people here are standing on the opposite blocks. This person standing on the footwall, this person standing on the hanging wall, which slid downwards relative to the footwall, exposing the fault surface. Tensional stress acting on the crust can cause brittle deformation, making normal faults. And given enough time and enough slippage, with each slippage event, we have an earthquake. So with enough time and enough earthquakes, we can build up mountains from A to B to C. That could be 10 million years of time. But if eventually movement along the fault slows enough or stops, the destructive forces of weathering and erosion will wear down the mountain. So you can have a mountain building episode that lasts some tens of millions of years, but eventually movement along faults will slow or stop altogether, and the mountains will get worn back down. Compressional stress causes the hanging wall block to slide upwards, and this gives us reverse faults. So my blocks again, if I push them together, we see that the hanging wall will always slide over the footwall. Compression results in sliding upwards along the footwall, and that gives us a reverse fault. The movement is the reverse of what we have for a normal fault. So compression forces the hanging wall to slide upwards along the fault surface or the dip of the fault. And again, these are from compression. Reverse faults are the name given to all, but if the fault surface or the dip of the fault is low and close to horizontal, then we can further describe the reverse fault as being a thrust fault. That's a pretty common term, so that's why I'm including it here. Here's a nice photograph of a reverse fault. The fault surface being in red, arrows indicating the direction the rock are moving on either side of the fault plane. You could probably tell by looking at this for a while. This stratigraphic unit here used to be connected to that one there, and they've been offset from one another because of movement along the fault. Strike slip faults. The strike slip faults are different than the vertical fault in that the movement is horizontal or lateral along the fault plane. So instead of having movement that's either downwards or upwards, the rock is moving laterally or horizontally. Now, as you can perhaps get a sense, when I do this with my hands, it's a little bit difficult to perceive which side is moving, or even to perceive the movement altogether. So when we deal with horizontal faults, instead of observing and discussing them in a cross-section view, like I've been doing with these blocks, we instead talk about them from a map view perspective. So where my fingers are, this is the ground surface, which I'm going to rotate so you can see it in the camera. And then we would talk about them moving from the map view perspective. So if my fingers were all, or should be continuous and connected all the way across, when they're not, because of a shift along the fault, we can recognize that movement has occurred along the fault. Always the result of shear stress. This gives us right lateral strike slip faults and left lateral strike slip faults. The difference being is how objects on the other side of the fault appear to move due to movement along the fault. So with a right lateral strike slip fault, movement appears to be to the right as you look across the fault. While with left lateral strike slip faults, it's the opposite. Movement appears to be to the left. So I'm going to model that here using this model I have. And I'm holding my computer now, so this is a little bit wobbly, excuse me, but I think this is the best way to show it. Okay, so you can see the model, and again, we're looking at it from a map view perspective. We have a road with a couple cars on it, and then we have a river. And these objects, the road and the river, they should be continuous and connected. But if movement along the fault causes them to be disconnected, we know that some deformation has happened. Now in this case, considering what I said, is this a right lateral or left lateral strike slip fault? And in this case, this would be a right lateral strike slip fault. Okay, the reason being is, I'm going to move this a little bit so I can watch myself here. If I was standing right here, looking across the fault, the road has appeared to move to my right. So imagine me as a person here, standing looking across the fault, wondering what the heck happened to the road. I would have to look to my right to see the other half of the road. And it doesn't matter if I'm on this side of the fault or on that side of the fault. Okay. Movement appears to be to the right. Hold this again in a different manner to make sure I'm demonstrating what I need to see. Okay, so as I look across here, maybe I should say as John Lennon looks across here to the other side of the fault, the road appears to have moved to his right. Same deal with the river. Looking across the fault, the river has moved to his right. With a left lateral strike slip fault, it's the opposite. So let's put it back together again here. Driving along the road. An earthquake happens, so much so that the road has been broken in half. John Lennon comes out of his car, walks over to see what happened to the other side of the road. Looking across the road, he notices that the road is moved to his right. So that would be a right lateral strike slip fault. If the movement again it had instead been like this, then that would be a left lateral strike slip fault. And again, it doesn't matter what side of the fault he's on. Looking across, movement has appeared to be to the left. The most famous example of a strike slip fault is the San Andreas fault, which is a right lateral strike slip fault. So here is a right lateral strike slip fault in Death Valley. The fault is illuminated by the red lines, by the red dashed line, excuse me. White arrows indicate which direction the blocks of rock are moving on either side of the fault. So if we consider that the white rock unit there should be connected at one time, this was here, but it has been shifted by movement along the fault. If you were standing there looking across the fault, you would have to look to your right to see where the other half of the strata has been shifted. Okay, I'll include this. You can look at this after I've saved this to our files if you want to do some review. Okay, so a quick review of what we discussed here. We have two categories of faults, the vertical or dip slip faults and the horizontal faults. Vertical faults include reverse faults, which are always the result of compression. They're sometimes called thrust faults if they have a low dip. Normal faults are the result of tension. And then the horizontal or lateral faults are always from shear stress, and they're either called right lateral strike slip faults or left lateral strike slip faults. And then we have a fault animation there that you can take a look at if you'd like. Okay. Let's look at some photographs here to quickly review. So here the rock has been bent into an anticline and a syncline. So what type of deformation would that be? That would be the plastic deformation because the rock has been bent. And as you might remember, bending rocks into folds is always from compressional stress. Here we have a break in this body of rock. Breaks are from brittle deformation. I've indicated which side is the hanging wall, which we see if we look at this for a little bit, has slid downwards along the fault. This should be connected to that. Because the hanging wall has slid downwards relative to the footwall, by definition, it would be a normal fault. Normal faults are from tensional stress. The rock here has been bent. It's been bent into an anticline fold, so that's plastic deformation, which is always from compressional stress. This is just a drawing, but it shows the rock has been broken breaks are from brittle deformation. Because the hanging wall block has moved upwards along the fault, that makes it a reverse fault. Reverse faults are always from compressional stress. Here the rock has been bent into a fold. Folds are always from compressional stress. Here, this drawing shows that the rock has been broken and is sliding along faults. Brittle deformation. And the answer is right on there. But if you look at this, you'll see that it is the hanging wall in all cases that is sliding down relative to the footwall. That makes it a normal fault by definition. Normal faults are from tensional stress. So what if a geologic structure is below ground and out of sight? Okay. And the answer is to make a geologic map. So a significant component of the study of geology, and this is something that you would do if you were an earth science or geology major, is that you would learn how to make a geologic map. And we do this because they give us information as to what is happening beneath the Earth's surface. What is the structure of the rock below ground and out of sight? So here we have an example of a geologic map. So geologic maps are made from the pattern of rock bodies where they intersect the Earth's surface. And in doing so, geologic maps are used to interpret the underlying structure. So on the Earth's surface, it might look something like that. A geologist has come through this area and inspected the rock and noticed that there are different types of rocks exposed on the Earth's surface. There's a red shale, a light brown sandstone, a tan limestone, then the same sandstone, then the same shale, then the same sandstone again, then the same limestone. So what would explain that pattern? In addition, measuring the dip or tilt of the rock units has indicated that the sandstone is tilted 30 degrees in this direction. That same sandstone bed at a different location is dipping 85 degrees in the opposite direction. And then when we get to the third location of the sandstone, it's dipping 40 degrees back in the opposite direction from the previous measurement. So how could that be? Well, if we consider what the rock is doing in the subsurface, that would explain how this pattern was created. So we'll concentrate on the sandstone here. Here's the sandstone, and if you consider this a triangle made between the ground surface and the top of the sandstone bed, that would be about a 30-degree angle. So the sandstone is sticking out of the ground at 30 degrees. Then the sandstone here in space has been eroded away. What we see here again, and here it's diving down into the ground at a much steeper angle, about 85 degrees, if we consider that relative to the ground surface. Then over here, it's tilting 40 degrees back in the opposite direction. Again, how could that be? Well, it's possible if this bed is folded into a syncline. and was folded into an anticline here that has been partially eroded. So the geologic mapping allows us to interpret what's happening in the subsurface. So how to make a geologic map? Step 1, determine the geologic units exposed on Earth's surface. Step 2, determine the contacts between geologic units. Take a look at this illustration here. So the geologic map, as is the case with all geologic maps, is colored. The different bands of color indicate different geologic or rock units. There's typically an explanation that lists the rock units from youngest to oldest. A contact or geologic contact is where two different rock units are touching one another or are in contact. So in this case, this is the contact between the green and blue rock units. As we see by the bands of color, they make an interesting pattern. So what could explain this interesting pattern? Here is the real life version of what is represented by this geologic map. This photograph is not exactly from the same perspective as this, but you might be able to make the connection between the two. So this is in Wyoming. We have this mountain with rock units that seem to wrap around it like that. So this is rather unique and would prompt curious minds to ask, wow, that's interesting. How could that be? How could that have formed? In order to answer that question, a geologic map was made of this area. Analyzing the geologic map and considering how the rock units are tilting or dipping, this is the explanation that we get. That it is a anticline, so a folding of rock units has also been tilted, or anticline has been tilted into a plunging anticline and then eroded. The end result of that plunging anticline being eroded is that you get something that looks like this. I'm going to expand on the types of contacts that can exist between two different geologic units. We have both conformable and non-conformable geologic contacts. Conformable contacts are when you have one sedimentary bed resting atop another one. That is a conformable contact. A non-conformable contact exists when you have dissimilar types of rocks in contact with one another. This one with the wavy line pattern to it is a gneiss, Precambrian gneiss, Precambrian being the geologic age of that rock unit, but let's not worry about that now. Gneiss is a very common metamorphic rock. These brown layers in this grayish blue layer here are sedimentary strata. Sedimentary rock is one type, metamorphic rock is another type. So there's two different rock types in contact. We call that non-conformable. When magma has come up and rose up and intruded into pre-existing rock, in this case sedimentary rock, we call that an intrusive contact because the magma rose up and intruded into that pre-existing rock. And the fourth contact here is a fault contact, when two different rock units are brought into contact with one another because of movement along a fault. Okay, I'm going to end the lecture here, and these are some additional assignments that are going to come up on in your module. But for now, the units that the exercises that I have listed in the module are the ones that you need to worry about for today. These guys are yet to come.